Welcome to this navigation lecture, a new lecture, as I mentioned, that I haven't practiced, so we'll see how it goes. So what's navigation? What are we talking about? So far we talked about how vehicles can reach targets while avoiding obstacles. So that's motion planning, or ultimately including also realizing the motion in many of these cases. And we looked at different ways how the system knows about targets and knows about obstacles, right? In the what we call the subsymbolic approach, there was actually information about the obstacles from sensors. In many examples, the information about targets came from a map, from knowing somehow where that was in some reference frame. And there are examples that, one of which I discussed in the winter semester, where there is also sensory information about targets. But the most common idea of how to autonomously move as a vehicle, and an idea that is actually also very connected to how animals move around the world, is that the information about the places you want to go, which I call targets here, would be coming from a map. So a map that represents locations in the world that are relevant to you. If you're an animal, maybe those locations would be where your home base is, or a safe place, or where some food is. Maybe obstacles might be where dangerous spots where there might be predators, or maybe like for mating, where someone who you want to mate with is, or like your offspring where you want to protect, and so on. So already you see, we'll come to that. The maps are about stuff that's relevant to you. It's not necessarily the physical map of everything. It's about what is relevant to your behavior. So it's a source of information about targets and maybe other kinds of behavioral constraints. So first I want to talk about the idea that you're using some form of map, and then I'll actually say more specifically what a map really might mean. And whenever you want to use a map, then you have to know where you are on the map, right? You all know that when you actually use a map in the conventional sense, that the first task is to know your current location on the map, where you are. We call that sometimes ego location estimation, or ego position estimation. That ego position estimation actually is always about three things, right? It is about two-dimensional coordinates on the map, so your position on the map and your orientation in the map. And remember, I was saying vehicles have these 3 degrees of freedom, even though they have only 2 actuated or mechanical degrees of freedom, and it's this non-holonomic kind of situation that you can still achieve 3 different things. As a human, for instance, you can rotate on the spot. To know and to use the map, you have to know both the position and the orientation. And then as you move somewhere, you have to be able to update that position on the map, right? And so I'll take this apart now and look at the different components. So one component is how you do this updating. And that's what I'll start with. This is the notion of dead reckoning or path integration, a couple of different words for that. And so that's a very, so let me first say what that is. So here's an example from a neuroscience paper, but involving here a rat. And so that illustrates the idea that if the rat somehow knows in which direction it is moving and knows how fast it is moving, then it could integrate that information, and it would have to keep track of time. So it would know I moved this long with this direction and distance and speed, and then this long with that direction, speed, and so on. It could predict where it is just based on integrating that kind of information. And then you could measure, for instance, that it has successfully done that by checking if it can go home straight. It will actually stop at the right location. That's a standard paradigm, how you actually experimentally probe path integration. And of course, when you do it with an animal, you have to make sure that there are no other cues to where it came from other than just this information. So that's just to define what that is. So that's a method that is ancient. That's in the history of mankind. It's one of the oldest sort of uses of geometrical methods for practical purposes, it's of course critical to moving around in ships, right? Sailing around in ships, where the word navigation comes from, right? That's literally, nav is the Latin source, is root of for ship. And so I was actually in the Navy, so I was actually a navigational officer for a little while, and so I actually really did that in practice. So that ancient notion is that you have information about your heading from your compass. So you know how your ship is oriented relative to north. That's one of the first inventions. Before we had a compass, for instance, some of these specific islanders who were able to navigate along very long stretches of not having any visual information on landmarks. They use the angle to the sun estimated in some ways, and then they need to know the time of day also for that. And at night you can do estimate angles relative to some stars that you know, and also you need that the time of day or night in order to know what that means to compare across different instances of that same situation. So that will be how you get your angle. And you would be estimating your speed through the water. I don't know if any of you knows that that's where the maritime tradition of measuring the speed in knots comes from. It was literally a very long rope on which there would be knots. You would have put some knots into that at certain distances that were measured. And at the end of that rope, you have a wooden board that would vertical to that rope, so that board would tend to rest in the water. And what you would do is actually throw that board into the water, so that it would, would break and be, come to zero velocity against the water. And as your ship is moving, you would be letting the rope run through your fingers and count the knots. How many knots in a unit time? So you have to know time. You have to have some way of measuring. For instance, you could do that by counting, or having a hourglass watch. So that would say maybe 1 minute or less than that, and then how many knots went through my finger, and dividing the length of the rope as multiples of these knots by the time elapsed. Your speed. So this unit of measurement comes actually from that. The tricky part is that then when you stop, you need to get that wooden board back. And so there was actually some mechanism, how a sharp pull on that rope lets a connection sort of slip, and the board would flip, and then you could pull it out. I actually worked with a historic artifact like that as a demo on one occasion. So that's how you would have an estimate of these two things. So you need time, speed, and your heading. And based on that, then you can make an update of your position on a map. If you know where you were initially, you can literally make that kind of computation. Right? And when you do this, even today, there's some simple drawing tools where you do exactly that on the map. And these maps used for nautical navigation are actually arranged such that they're good with the angles, because they're used for this. As you know, because the Earth is actually round, you have to sacrifice one quantity that is invariant, and that is actually distorted. Sorry, and the Mercator projection is actually about that, about being correct with the angle, so that you can do this navigation very well. And of course, today this is something that we have many technical implementations of, much better, of course, than these old methods. You might know that, for instance, currently in this terrible war we're having, there are these inertially guided systems. So they have sensors, not just of velocity, but they're typically of acceleration, that they can measure very well, like from the forces that occur, the little piezos in there that sense these forces and translate that into acceleration. They have very precise. And sometimes you can actually also use your actuator signals, because if you have a good model of your plant, you know that what state change is brought about by your commands. And then you can use modern techniques, Kalman filtering and so on, to integrate both prediction and measurement in an optimal way and so on. So these systems are quite good today. And there are many uses of that. That's also how, for instance, even your iPhone interpolates in a way between events where it can reset itself, and I'll come to that in a moment. So even though these techniques are all very good, there's still the fundamental problem of path integration, dead reckoning, that uncertainty accumulates in time, because it's just adding. Integration just means adding. Discrete time will be adding. And so if there's any uncertainty in your estimates that you're adding up, that uncertainty just accumulates. There's no way to compensate for past errors, so to return to a value closer to truth. I've sometimes in the winter semester shown this example. This is Brownian motion. So it is the evolution in time of some variable. In the lecture, that's actually activation as a function of time, and they all start here at the same point. And what happens here is that at every moment in time, there is a random kick. So a random velocity component is added to the velocity, and that velocity is integrated, right? So it's the equation u dot equals white noise. And that's the mathematical model of Brownian motion that Einstein famously studied. He proved, in fact, in some limit case, that the variance of a process like that increases in time. It depends on the dimension of the space. It increases like a square root in the usual three-dimensional space that we're familiar with. And same in 2 dimensions, a bit different in 1 dimension. As you see this here, that in different runs of the same simulation with different random seed for the random number generator lead to different outcomes. And you can see visually that late in time, these different traces are further away from each other than here. And so this is just the effect of chance. Maybe somewhat intuitive. If you get some random kick, you end up, let's say, in a position up here. From then on, the probability of getting more kicks that push you further away is the same as the probability of getting kicks that move you back to your original position. And so you can see that over time, you have more and more opportunity to explore further from home. And there's no systematic effect to undo that. In fact, in the winter semester, I talk about how stabilization is actually exactly what is needed to limit the growth of variance. So this is a very, very well-known problem. So that's why I was mentioning these Pacific Islanders, because the longer the distance, implying also the longer the time during which you do this kind of dead reckoning, the more uncertainty you accumulate about where you are. So what you really need is some method of resetting your estimate. We sometimes say recalibrate your estimate. And that amounts to doing what I initially said about having some process of finding out where you are on the map, right? On recognizing your location on the map. So that classically is done by associating with a position on the map particular information. So in, for instance, nautical situations, you have landmarks. That is, there are some points in the landscape, the location of which the map maker knew, like a church or a lighthouse or some other item like that you can recognize visually from your ship. And if you recognize at least, actually with 2 such things in 2D, you can actually estimate where you are, but you use 3 typically to have some estimate also of your error. It's called then triangulation. So that's based actually on knowing where, in which direction these landmarks lie relative to some reference frame. And on a ship, it will be, again, your compass or relative to the sun. So based on that, you can actually estimate where you are. That's the constant task of somebody who does so-called terrestrial navigation. You can do the same with respect to stars, actually. And of course, in modern days, it's not really done in this very simple way. So sometimes it's done very analogously. That is, you have special beacons that set out special signals, for instance, radio signals and so on. This is done, for instance, in aviation, where you have essentially active beacons that send out a particular radio signal, and you can have some angular information through something I don't want to explain in detail. And of course, you all assume that you just have GPS, and GPS, of course, is actually also based on the principle of triangulation of that same kind. I don't want to explain the details of that. And so that's a topic that I'll come back to, what the more biologically inspired way of doing that is. Before I do that, I want to talk about how animals and humans do that reckoning and path integration. And you find that everywhere in the animal kingdom. I'll show you two examples. So this is from humans. This is an interesting study. Someone called Loomis studied this for a long time. So what people do, for instance, is really set up that triangulation task. So people are, for instance, blindfolded in a position, and the experimental assistant would, for instance, take that person by a hand and lead them along a path, for instance, lead them along a straight piece, have them turn on the spot, lead them along another one, leave them off, and then the instruction is to return to the initial position. So people have to walk in a certain direction, close the eyes, and stop when they think they're back home. Yeah? And people can be quite bad. They go somewhere here. So for instance, a typical experimental paradigm would have different such triangles, from this one, and then you can see, including this one and the different distances. So this is the grid of points to which you will lead the person from that initial location. And then, these traces here are where people actually went after they were released that way. And you see from this one example, you can really see a lot of interesting things. So the perfect system would, all the paths would converge here onto the cross, right? You see, this is actually a case where that's very poor. Kind of interesting that you see that people are relatively uniform in the direction in which they're heading. And that already hints at some difference between how directions are dealt with and how distances are dealt with. But there's also actually some correct aspect, like this direction here is, this path is shorter, and this would be a case where the horizontal distance isn't very close, while there's a long path here. So there's some measure in the length as well. Here's a fun example. This is each is a different participant. And so you can see with the naked eye that there are some good navigators, like here, look, this one is really nice, and this one. Then there are some rather not so good ones, like this one here. So quite a lot of variance. And this study actually probed specific questions, like is there a difference between congenitally blind and people who are blind from an accident, or a control group of non-blind people. And there has been a long story in history that congenitally blind people have not developed the sort of the reckoning techniques, because they don't get feedback from landmark recognition that I'll come to next. And that study actually had a non-effect. There was no significant difference between these different groups. So I showed this. First of all, there is some, this is better. It's not like they're going in random directions, right? So there's some evidence for that reckoning. It's actually surprisingly difficult. You can try this yourself. It's a nice party game, by the way. Have a large enough room and you can play that game. It's really fun. But we can do it to some extent. Humans are not particularly good. There are some animals who are very good with that. A very famous example is the so-called desert ant. It's a small, it's an ant that lives in the desert. And the desert sand is particularly poor in visual information. And it's evolutionary optimized because these ants live in like canals in the sand. And they go outside to forage. So I don't know exactly what they do out there. But they have to go into their home base very quickly. Don't remember the exact number, but they can only stay outside in the sun for a brief moment in time. If not, they dry up and die, because it's so hot. And therefore, it's particularly important that they find their hole. Remember, it's just a hole in the sand, and there's no good landmark for that they find it quite quickly. And in these, they're interesting experiments. Someone, Rüdiger Wehner in Zurich, did a lot of experiments with these animals, where you can, for instance, through some stimulus, make them go out, and then you can motivate them to go home. Actually, they will do it spontaneously after some time, but also you can make a danger signal, and they will go straight home, and measure how well they find that hole. And there's the fun information that the next thing I will talk about, landmark recognition, that they don't use it while they are running home. They're just running home until that reckoning is at 0. And only then they start to use visual information. So for instance, what they did is they would just shift the ant, set it off its path. So it shifted against its original position. And in such a way that it would be actually on the way back, it would actually pass by its home. But because the dead reckoning vector isn't at 0, it actually just goes through and just stops where by path integration it would have been home. So there are some animals that are very specialized in this. And there's also some work on 3D path integration, which also works. I'll say more about that as I talk about the technical solutions. So that's one system, and so that is used by animals, and it is used pretty much by every navigation algorithm. It's sort of a short-term, analogous to the reactive layer that we talked about earlier in path planning. It's sort of the low-level interpolation method. So even if you may have methods to know where you are through some recognition, you would still use this to interpolate between different locations like that, because it's quite natural that you would not be able to triangulate at every moment in time, that you would do that at a certain discrete moment in time when you recognize where you are. So that resetting is based on something that the general term for that is landmarks, that is on some form of sensory information that is then associated with a place in the map. Or we say when where I have that sensory information, then I'm in this spot on the map, and the map is made such that that's the case. Now we'll talk in a moment about what happens when you make the map yourself. So, because we think of landmarks often as objects, this comes from this nautical tradition that you're far from the object and recognize the object, and you know where the object's on the map. And that might be when you navigate yourself in a city, you might recognize a particular house or the church or places like that. But actually, the term is used in a much more general sense. You'll see that in many of the animal examples, including human examples, you're not actually using objects, but you're using something like views, like a panorama view. So for instance, if you're in a particular location in town, you have a certain view around you where maybe the individual objects that you recognize. So it could be a view that's built conceptually from discrete stuff, but it could also be a view that is just a continuous view. And there's actually some evidence that humans can estimate their location and their pose and so on, things like that from views. Here's a reference to an experiment. There's a lot of literature. I just wanted to put some illustration here where people are probed at different locations, viewing certain scenes, and then they have to estimate where they are. And they can do that to some extent. There's a lot of information about animals using views like that. And I'll talk a little later about place fields, but there is sort of one interesting thing is, again, with these ants, there you can see there's nothing neural we record, we just record the behavior. So the funny thing with these ants, again, Rüdiger Wehner's work, I hinted that you can make them be lost by just shifting them off the path. And so they end up somewhere where their hole is not, and now they need to find it. And so they are making some kind of search behavior. And you could have some landmarks actually, or create a certain panorama by putting some objects around the hole, and they will be familiar with that because that's when they built the hole, and they've been living there for I don't know how many days. There are always these like a certain wooden blocks you put into the little terrarium. And now what you can do is you can around this new location, you put up these blocks, and you can put them actually at larger distances or at closer distances, so that when they're at larger distances, right, that now the view that that's consistent with the view they had originally is preserved if they move within a larger area. That will be the area of the similarly distorted views, and you find that then the animal when these landmarks are further out, the animal will actually explore a larger region around that lost hole than if they're closer in. So that suggests that the criterion they have for exploring space is based on how similar the view is to the view they stored. So not categorical about the objects per se. And there's also neural data like that, the place fields that come to that have the same property. So there's a lot of work about that. So that's actually the dominant picture in neural thinking about how you know where you are, that we're using a distribution of sensory information that could be a panoramic view. We humans clearly also use discrete objects within such views. It's just the raw view, but we're looking and we're classifying these views somewhat. So there's a lot of work of how people recover after being lost. And again, you can make similar measures, and then you see that people pay more attention to certain things than to other things, for instance, to objects or aspects of the environment they are familiar with. I'll come back to that at the end of the lecture. So what are maps? So maps ultimately are associations between information about places, as I just hinted, from which you have certain views. Here, this is from a paper where it's really associated with objects, to make it intuitive. But I'm also saying, it would be a location where, when you are there, you will have that view, for instance. Or you could even say, when I'm there, maybe I have a certain smell as an animal, for instance. You would maybe associate a smell with the location. And these maps can, there's all kind of work about, are they really metric? So is it a map that reflects really the distances and the angles, or are they graph-based that is more topological, more knowing who's the neighbor of whom, but not really in absolute terms, or it's a combination of both? The way that, so in animal works, you very typically find that animals go particular paths. I'll come actually back to that again a little later. And then that is very suggestive of having a graph-based representation. There's some work in humans that where essentially you ask people to provide estimates, for instance, to really make a drawing of a town they know. And you find that then the metric structure of the space they draw is strongly distorted over the actual physical map. And it's distorted in a way that makes a lot of sense. So for instance, if the path between two locations is long because you have to go over a bridge, or it goes uphill and downhill to go there, then people tend to draw these on a map at a larger distance than the physical distance. Very interesting stuff like that. There's a lot of work on that. So there's been a debate for a long time about whether we can really be sure that animals actually really use a map to navigate, because they are very simple alternatives. So even the classical experiment, some of you might have heard Tolman, who's often cited as the inventor of the notion of cognitive map. He made an experiment where animals had to choose among a number of different entries into a very simple labyrinth, and only one was right. And actually, it turned out that that experiment didn't probe perfectly if it was the animals really using a map, because there was some sensory cue to what the right direction was. So for instance, if you had a situation like you're navigating on a map like that, you could also imagine that rather than really know the map, you have just remembered a sequence of stimulus response associations. So that would be, for instance, a description that to go to the university, when I see this sign, I turn left. When I see that entry, I go in. When I do this, then I do something else. So it would be a chain of stimulus response associations that would take you to the university. And so successfully reaching the university would not be evident that you have a map. And so the convergence view now in a lot of the animal literature is that a map is something that you can use freely. You can generalize, in other words, over those stimulus response chainings or location chainings that you experienced to build the map. So technically speaking, you can do shortcuts. For instance, this from a paper by Pierre Pousset, who was my colleague in Marseille, where he illustrates experiments where a dog, in this case, learns a connection between two locations and that between two other locations. And the critical probe is, can that animal actually find that there is a shortcut to go from A to B on a direct path or multiple paths. This can be done in experiments, for instance, because there is a blockage initially, so you can't go directly, and the animal learns to go through this. And when you remove that blockage, will the animals actually take the shortcut? The interesting subtle stuff, for instance, from this group, they had an experiment where cats actually navigate in like a labyrinth, and they go through the food and they've learned how to get to the food. And then there is a possibility for a shortcut. And under some conditions, the shortcut is blocked, and it matters if it's blocked by glass so that they see the food, or it's just blocked and now they have to take a longer route around it. And in these cats, when there is when they can see the food, they can't do the longer route. They kind of get stuck there and try to go through that glass. So there's a lot of factors that play a role on how to actually assess this. But that's sort of the standard notion that we have evidence that animals use maps when they can find paths that they did not experience in building the map. And animals, of course, always build the map themselves by exploration, right? We cannot download it into their brain. Good. And we generally, of course, think of maps as something that we can use to navigate to places we've not been before. So this other problem is how to build the map. Is, in these historical examples, this is a separate process. Somebody is using, other means than the ones available for navigation to build the map. While in robotics and for animals, we want to do the map building as we're navigating. So it's sometimes the acronym SLAM is used for that: simultaneous location and mapping, localization and mapping. This is from a review paper by Durant-White and Bailey, or sort of Durant-White is like the wise old man of this field, about the SLAM problem. And so generally the idea here, the white stuff would be the ground truth as it is said. And so generally what the nature of this problem is that you have some estimate of where you currently are, which could be off. You can use that reckoning to update that estimate, so that could become less and less precise. And when you are at a new location, you might have some way of characterizing a landmark you detect and associating that with the bearing, the measured distance, different ways of doing it, different distance, angular distance, or and maybe also metric distance if you have some measure of that, to associate some number with that. And so then it's a discrete locations along your path, and so you would slowly build a map based on your estimates. But that map, of course, is also based on you having estimated where you are when you did make the entry into the map, and that was based on dead reckoning from your previous location. So over time, the uncertainty increases. So there's a whole, essentially two big problems there. One problem is to optimize the path integration, so you can use the change of these bearings as you go to improve your dead reckoning. So don't do dead reckoning just in some motor measurement from your wheels or whatever it is, but really use the landmark information also to do that reckoning. There's a lot of work on that. And then there's the problem that's called loop closure. I didn't quite find the figure where it's actually close. So you can imagine that if you make a map like that, this is from many runs, the blue is the runs, and then you build estimates of where you are and entered these landmark kind of information, piece of information into your map. And loop closure would be then when ultimately you're reaching a location that you explored at some earlier moments through a different path. For instance, if you move further, you would maybe arrive at this location. Now, at some point, you have to say, now I'm recognizing a place I've been to before that's very far from my local position. So I would not use it usually to update my current position. And I'm saying, oh, this must mean that I'm in that same part of the map I was earlier, and that by that time along, that reckoning error has to be corrected, and you have to sort of close the map by reconciling these two different ways how you characterize the same location. And there's different mathematical procedures for that I don't want to go into. So that's the SLAM problem. And so animals are supposed to also solve that because they are, of course, building their maps based on running around on their own, right? So they are doing SLAM in some sense. Good. So that's sort of the basic concepts, what verification means, and that reckoning as the core method, and landmarks, and the resetting of landmark relative to landmarks, and then the building of the map itself. Now, I will take you now through an example of how to use the concepts that we developed so far in the course to deal with the SLAM problem. This is sort of old work from my lab here, done in 97, ancient. And that was actually inspired somewhat. I was in Marseille I did this work actually in Bochum, but I worked in Marseille at the time when we wrote this paper. And where there were people actually working on hippocampus, and I'll actually establish the link to these neural maps at the end of the lecture. So what the link to the familiar is that the path planning, so when the vehicle is moving around, that will be the kind of dynamics you're familiar with, heading direction and integrating that. And then we'll be looking at two things. We'll look at a procedure to estimate your ego position and how to integrate that with information from some form of recognition of where you are when you build the map. So a network of discrete locations we call home base is the map, and the system was built the map by itself, and it uses, whenever it's close to one of those places and recognizes that place, it uses that to reset itself. And as it does that, it then can sort of reset the dead reckoning system that does the ego position estimations. Our special thing then was to do all of that just with dynamical systems. So unlike a lot of the approaches out there that use different, estimation procedures and algorithms and so on, we did it all with dynamical systems. It was aimed at being a model that would really be neural dynamics ultimately. And this was actually before we were just around the time when we started using dynamical field theory. And in the meantime, we're of course using that. And I'll show you at the end of the lecture how this connects to people who actually do the same sort of thing with neural dynamics. So the examples we have here are just dynamical systems without necessarily a valid neural interpretation of these systems. So here is sort of a survey over this architecture that I will be showing you a couple of times. Here is sort of the core for behavior. So the behavior variable is the heading direction of the vehicle that you're very familiar with, and the speed along the path, right? That I often hinted at. That's also something you want to control. And it's at that level that you get sensory information, for instance, about bearings of particular locations. You can do obstacle avoidance and so on. And this goes to the motor system. So you're actually driving the vehicle this way. There's a user interface where we can set goals for the system. So in this simulated model, there was some actually physical implementation of that model as well. That's goals are set by a user in the map. And so that's the action level. And then there is a level that I call it that reckoning, where the system does path integration, and it actually does that based only on its own motor commands with some estimate of error. And the time is assumed that you can integrate. So it's real time. You always predict the position at the current time. And that gives a estimation of the position, XY, of the vehicle and its orientation. The little arrow here is supposed to be the heading direction. So it's this arrow here. So of position and direction, these three variables of the vehicle at different moments in time. And then on the other hand, we would have a system that I'll explain where we would be associating visual information about the environment, 3D, so 360-degree views with particular locations in the map. And these locations would be taken essentially from the dead reckoning, but we have an integrated layer, a layer that combines what we get from vision and what we get from dead reckoning. And so sometimes it will be dominated by dead reckoning, namely when we don't have any view information. Sometimes it will be dominated from the views when we actually recognize that we're a particular location. And so this is used to set the any landmark information here. And once you have that, you can use that to influence the system when you recognize that location. And whenever you don't have that, you always get this input from the dead reckoning system. So it's essentially using the views as a way to recalibrate or reset the dead reckoning values. So I'll take you through some details, not in very technical detail, but some details of that. So our initial work was using this in simulation.
I have a question.
Yes, please.
Did I understand it right that the integration is a part needed for the dead reckoning to interpolate or extrapolate the way and direction of obstacles or targets, or?
No, that's not correct. And I see that actually somewhat confusing terms we use there. So dead reckoning itself does integration, as I hinted earlier, right? So the step from here to here is integration. Namely, if you have phi dot, then you can integrate over phi dot to estimate phi. And if you have, phi and the heading and v, then v is x dot y dot, and you can integrate that to estimate x and y. So there's integration from here to there. That's the integration that is inherent in the reckoning. We call this layer integration layer, but it should be called maybe fusion layer. So it is a layer that essentially is about combining the estimate from that reckoning and the estimate from visual recognition into a fused estimate, and we call that integrated estimate. So that's actually a very unfortunate term, but it's meant.
So it's not a mathematical term in this case.
So it's actually, no, this is not a mathematical term. It's just a functional assignment to what this layer does. So it's very unfortunate. We should have called this a fused position estimate, and it means fused. It's really sensor fusion, if you know anything about that. So if you have multiple sources of information about a variable, fusing them means computing some combined value that could be just averaging, but it could also be that under some condition you just vote for one as the correct one, and sometimes you vote for the other one. And maybe it will become clearer when I actually show you how that works. Okay. So that's okay. Good. So unfortunate term. So this is just the fusion layer. So in the example, in the first implementation, we made a very minimal kind of system. This agent was moving around in an arena. We had some outer boundary just so that it doesn't run off into infinity, which the agent would sense as an obstacle, so that it would be repelled from the outer boundary. And then we put some objects, actually this boundary here, this actually acts as, this inner boundary acts as an obstacle so it doesn't go out. And outside that, we put some objects, and they are just there to create some visual panorama. So the one-dimensional view from this robot was simulated, was such that it would have essentially a certain value when, from the agent's point of view, its view hits a surface like that, and in between it would have a different value, like zeros and ones, black and white, whatever black and white checkerboard pattern. We actually only looked at the derivative of that, so it would essentially detect these edges, so an edge here, an edge there, and so on, as a function of angle. So it was not, there was no height measure, it was just a one-dimensional view, but 360 degrees. So that's the views. I'll show you an illustration of these views in a moment, on which we base visual information about place. And then our idea was that we store such views only at particular positions in the plane, discrete different positions. We call these home bases, and we had a discrete number of these, and we actually had some way of self-organizing when it makes a new home base. Within each home base, actually, we had multiple locations. I think it was 10 locations at which it would be storing these 360 degrees views. I'll be coming to that in a moment. So that idea to have these discrete locations was actually based on some biological information. Actually, I interacted at the time with someone called Ilan Golani, who was an Israeli. He's still alive, but no longer active. He's a researcher in Israel who does ethological work, so observational work, and he, with his team, did a lot of studies where they had animals, mostly rats, sometimes mice, run around different territories, arenas, and so on, and they would just keep track of their behavior. Just give you a very rough view of that. For instance, in one study, they had an arena like this, and they would actually have smaller squares here at the boundaries and larger squares at the middle, and they would be scoring every time, so measured time units the animal spends in any of these locations. So that's a way to discretize the space. And from observational data, a camera where you track where the animal is, they would be scoring histograms. So here you see some histograms of that, where they would be scoring how often the animal is in which of these parts. You see why they used smaller squares here at the boundaries, because the animal spends a lot of time at the boundaries. And the upshot of this in a number of studies is that animals like that built a sequence, a discrete set of what they called home bases, or locations in space where they spend most of their time. And when they do that, they show particular behaviors, particularly this so-called rearing behavior. This is the rat actually sort of just rising up and literally looking around, really scanning the environment, which is presumably a method of, first of all, making sure there are no predators here, but also of really registering the view from that location to recognize that location. So these rearing behaviors are more frequent in these places than anywhere else. And then there are also certain behaviors like grooming that reflect the animal is safe, is in a safe place to do these kinds of things. And those are also associated with these places. That's why they're called home bases. In other studies, for instance, you can look at what happens when you startle the animal, and you find it will be running to one of those places. Like there's something like a principal home base that is really sort of the nest of the animal. And in other studies where they looked at outdoors, large territories, you find that these home bases tend to be visually protected. These animals all have birds of prey as predators. And so they want to have a place where they cannot be seen, like under some branch from a tree and other things like that. So there's a lot of biological criteria of how they choose these home places. And so here's an example where across time, there's a score here at which of a discrete number of such places the animal spends most of the time. And you can sort of see that it is spending a lot of time in one, and a few other places spends its time. It doesn't really roam randomly through the arena. Kind of important to realize, because I will refer to place cells at the end of the lecture, where you're sampling space in somewhat continuous ways, and you do that by motivating the animal to go to those places, and that is actually in contradiction to that. And this shows this little bit artificial situation, which is just induced by for experimental reasons. So that's where we got this idea of a home base from. And so around the home bases, we just stored these views. You see, these views are the spatial, so plotted here for illustration in a circle, but it's really a vector of the current view. There can be zeros and ones from these different backgrounds, and by differentiating, we have this plus and minus, so going from 0 to 1, from 1 to 0, and so on. And so these would be these different vectors, and at every base, we would store a set of such bases from slightly different locations within the home base. And I'm not explaining now how we decided where to build the home bases, which I'll come back to later. Now, when you have this set of home bases, so what does it mean to recognize where you are? Recognize where you are would mean that you compare your current view with the stored ones. So we stored them just in a computer sense. So it wasn't biological how we actually did this with some synaptic process or anything. So what you can do is you take your current view and multiply it with, as a vector, scalar product with any of these vectors you've stored. And if there's a vector with whom you have a very good match, in this case, it would be this vector, then you say, I must be at the location. It's possible I am at the location where I have that view, so that I know which home base I'm in. What's also illustrated here is that we actually did something sophisticated. I mean, every view that we had in a home base was not just stored. I mean, mathematics speaking was done a bit differently, but I can say for now, it wasn't just stored in one arrangement. It was also stored in a rotated version. For instance, this would be the original version. Then I would have rotated it by a certain amount of angular rotation on 2 times, 3 times, and so on until you're wrapped around. So you would have all possible rotations of that view. And so when you now find that the correlation is good, you have learned not just that you're likely to be in home base 2, but also that you're rotated by this much over the orientation that you had when you laid down that view. So that's how we don't have a compass. Rather than a compass, we find out how we oriented by rotating the view. Now, I have to ask yourself if that's going to work. And I have a couple of plots, which unfortunately in the rendering as a PDF from the paper are not so easy to see. So there was sort of a fundamental discovery we made, which one can perhaps see here in this plot. I'm not entirely sure. So this is the correlation computed between a stored view and the current view, when the current view is taken at different translational shifts from the location at which we took the original view. It's just along one line here. It will be 2-dimensional usually, and also rotated against the memorized view in different ways. And so you see a lot of this correlation is around 0. You see there's a nice peak where there is a good correlation. We have some threshold for what correlation counts as good. And maybe it's not so easy to see because it's supposed to be a 3D plot, is that there is a spatial receptive field or place field where there is here a whole profile where from slightly shifted locations you are getting decent correlation, so that you don't have to be at the exact location to get a good correlation. You can be shifted away from it to some extent. I'll come back to that in a moment. And then in this direction, in the rotational direction, you see there's also is a peak, but it's a very sharp peak that is in rotation. When you have a view like that and you just rotate it a little bit against the original view, then the correlation goes away. Now, the critical thing for that, I mean, that makes a lot of sense, right? If you have a view and you rotate it, then how quickly the correlation decays just depends on how high the spatial frequencies are, how thin the lines are that you pay attention to. Now, the critical thing about this is that the angular, the peak in the angular direction can be estimated at locations other than the best location. So even if you go like in here, and it's maybe not so easy to see in this plot, even if you're a little bit off, you still have a clear maximum along rotation at that shifted location. So that means the animal can, or the agent can estimate its orientation without having to be at the precise location at which the U was taken. So this decouples the angular estimate, so the compass function, from the positional estimate. And that's sort of in a sense, an ecological law. It essentially says those factors that determine your angular sensitivity are different from the factors that determine your spatial sensitivity. And the angular one being determined by the visual frequencies, how thin the lines are in the picture, while the spatial one I'll come to, that actually depends on how far you are from the objects that cause the view. And here's that story. So what we did here is do this thing I hinted at with the animals. That is, you would move out these landmarks that cause the view, but such that the view is the same at the same location. If you just scale the scene, make it further away, you can make that the angles that you see are the same. It's just blown up and the objects get larger as they move out, and the view is invariant. But when you move slightly, then the change in the view is not invariant. When the distances are very large, then as you move around, the view changes very little. And when the object is very close, if you move around a little bit, the changes are quite large. You can yourself look at a scene that's close to you, move a little bit back and forth, you see there's a lot of visual change. And then if something's very far and you move the same amount, there is much less change. Now, for instance, the moon is very far away, and when you move around, then the relative position of the moon doesn't change much. But a lamppost really changes a lot. It's visual appearance when you move toward it or away from it. And so here this is the operational demonstration of that. So this is one scale where you have a relatively sharp peak. This is now both translational shifts. So you see that the range over which you get a good correlation with the stored view is quite small. And then as you scale up the scene, as I hinted, then the range of distances over which you get a good correlation is much broader, get a more broader tuning field. So that's that says that it's good to use what we call distal views, distal objects. So those objects that are far give you a better range for your estimation of where you are. And that's actually something that is observed in animal experiments. Where you get it, the place cells I will be referring to are actually sort of like this correlation. They do something like this correlation. So in the what we did in this model, what happened in this model is that when we were entering a area where there's a home base, the system would start to get good correlations, and it would be able, based on that, to first pick out which orientation it has by finding the arcmax, the angle at which this correlation is maximal. And it could then use the correlation with a number of different views it took within the home base to estimate exactly where it is in space. And this distribution of correlation coefficients across the different views would essentially act as a weight in estimating the actual location. So this is like a population code or a peak of that combined correlations is then your population estimate of where you are. So I'm glossing a little bit over the details, but you can maybe imagine how that would work. So in other words, those views with whom you have very good match, they vote very strongly with the location that they are associated with, and those, like here in the middle, and those views that match a little less well, they contribute less to this contribution, so that the amplitude is smaller. And then if you compute the theoretical mean of that by taking the activation into account, then you have the estimate of where you are. That's how we did that. So this is almost neural. You could think of this correlation as being something that is neurally done. So neural networks are essentially computing a correlation between the synaptic strengths and the input, right? And so in some sense, you would say I've stored the views in my synaptic connectivity, and the current view comes in as input. And then what that neural network returns is a measure of the correlation between the view. And so this would be combining many such votes in a population code picture. Okay, so that's how this system here worked. And then when I say we estimated the location, it was really just by taking the values that were stored with these views when we acquired the home base, combining these in this weighted way and taking that value. So that's the value that's passed down to this fusion layer here. Now this fusion layer, again, we used the word integration, and one of you pointed out correctly that that's actually misleading. It's really just fusing these two. So that worked with dynamics. That was our special trick. So this is now a dynamical system of position, the estimated position, and we have a dx and a dy. And this is a dynamic, so dx by dt by x. And so when we have a strong estimate, we make a forcelet. So you're familiar with that? It's an attractor forcelet, right? Making here a negative slope at the location at which the view was associated. This just illustrates that you could have different estimates, and there's some theoretical reason why this is a very good idea. And the dead reckoning would give you a different kind of estimate. So the dead reckoning, this is the dead reckoning system. The dead reckoning system would have a dynamics that integrates. For instance, here you would have a positive speed, and that would mean that's your dynamics. So if you have a dynamics like that, then integration will just make a larger and larger value. Like if you start here, then over time, you would linearly increase your estimate. And that will be the dead reckoning, the integration, right? But when we have a negative slope, then we get an attractor, right? And then it no longer integrates. It actually then takes the value wherever that zero crossing is as the current estimate. So the trick was that whenever we had a visual estimate, we would erect an attractor in the visual system that would make an input into this integrated layer like this, and that would overvote the input that came from the reckoning system. And when we had that kind of estimate, it would actually provide a input to this dead reckoning system to set an attractor there, and that's how we would be resetting the dead reckoning system. That's roughly the idea. And it's technically speaking instability. That is, technically speaking, you have that as long as there's dead reckoning, then the dead reckoning system is dominant. And then when you have a visual event, it resets, and that means you makes the dead reckoning system unstable, and you can do the resetting. Okay. So that's how this integration layer works. So driven by this, but when there's an input from that, it not only resets this, but also that. So this is how all of that was worked together. So here's from a long run is a simulation. The agent here is this little thing, and the agent would be running around. These are places where it built home bases. We had an actual neurodynamics to decide when to do that. Or some complicated thing. I'll hint at that in a moment, but it's I don't want to explain here because I didn't even introduce neurodynamics in the summer semester. Those of you who know that from the winter semester, it's the dynamics of some activation variables, and they can make selection decisions. You remember that? That's what's underlying this. So a few features here of this. So this system, these things are obstacles that make the vehicle go in funny ways. Like here is a complicated obstacle configuration. And again, these dots are where it acquired views. And so we have the animal, the agent, built these views essentially when it notices that its uncertainty of dead reckoning has become a certain amount, and it's based on some kind of internal simulation, then it starts to build a new home base. And so this is a home base it built, and this is one, and so on. And then we did some test run. For instance, what we did here is when the system was at a certain location, I think it was maybe this location, we would just reset it in the simulation, right? We would just make the system jump from this location to that location. And then we study whether the system is actually able to recalibrate it. Here, it can't recalibrate it. We'll just keep integrating what it was previously integrating. We also rotate. As we set the system, we were also rotating it. So it goes in this direction because it was originally headed for this direction, for this target here. And by resetting it, it went in an off direction. We did it such that it would soon find a home base. So when it was here, it reset its estimate, and the dotted line is its estimate. So the system thought it was going here, and oops, but it was really going here. And at this point, it recognized this home base and reset its estimate, and then the dotted line is again close to the solid line, and that's how it ends up. You see, all along here, the dotted line is somewhat close to the solid line, so it always knows roughly where it is. We actually made the system go around different circles by giving it targets. Like we first give it this target, and then that target, and then this target. And the navigation, the path finding itself is based on what you know. Huh? Target is direct input to the heading direction, and then the obstacles are what make it go around in funny ways. That's why it goes around this target, and we want to find the entry point in the way that I had shown you previously. So the reset event, so here's this reset event, right? That's when there is a match, it has recognized the home base, and that triggers that transition I hinted at, then there is a reset event. And later we expanded this, and again, I'm just hinting at that. So for instance, we had a system that had a lot of different behaviors. All of those behaviors were done by dynamical systems. So not only target decision, but also selecting among targets. This is what I just showed you. Obstacle ones, it has some search, spiral behavior. It would, if it's lost, it would try to search. We had some exploration behavior, the actual snapshot learning, and this is when it's resetting. And then we have a major home base where it would be returning to if it was lost, and we had the method to create home bases and actually then planning trajectories. And when it was planning trajectories, it was always going through home bases to go to the trajectories as the animals do, and some other subtleties. And so it would actually really autonomously organize itself that way. So this is long sequence simulations, many hours of simulation time on the computer, where that system initially has nothing, and it builds these home bases. You see, it built initially here a home base, and then I think it builds one here, and then another one here. It's these little green dots. I don't know if it's so visible. There are some green dots here now. These are these places where it built home bases and so on. So the system will be running for hours and just always keep mapping, and then also use the map. Of course, we're only making the system use the map by giving goals from the outside, because this organism, this model, didn't have any drives or goals, didn't try to forage for food. It was just always running around trying to estimate where it is. So only by giving it from the outside targets would we probe its capacity. It's a really neat system. Now, the historical thing is that I started this work in Bochum in the 80s or early 90s, I believe. Yeah, 90s. And I knew about it because we were building robots. I had shown you some of these robot implementations earlier. And we were only very broadly influenced by biological thought. It wasn't really based on that. But then I moved to Marseille, where there was actually a group who was working on hippocampus and doing this work. Bruno Pousset was the head of that group. And I came to realize that a lot of the things that we had developed were really matching the neuroscience very well. We got close to making a serious collaboration, but then I went off into dynamical field theory and didn't really have time to deepen that. But since this field has really blossomed in the neuroscience, not influenced by us, right? We just stumbled into this. But it turns out that a lot of the things, sort of what like happened with the Bill Warren work that I was reviewing, that some of our ideas did match the biological ideas. And so maybe there is something deep about arriving at these ideas from a functional analysis. And so this well established in the meantime that some of the mechanisms we postulated are really at work in animal navigation. So I'll only give you some rough hints at how that works. So this is a review article by McNaughton, but it actually also has the Nobel laureates for this. I think both Mosers are on this, and I wonder who else is on that paper. So it's a very authoritative article about the path integration and navigation aspect of hippocampal place maps, and I'll highlight a few ideas. This is actually a paper that also reviews theoretical ideas. So for instance, I'll give you just a few highlights. So one thing is that there are some signatures of path integration, not directly, so it's not, you can't directly observe the actual mechanism. How does it use, what kind of sensory and motor signals does it use to do the integration? But there's evidence for that, for neural vectors representing that. So just to give you sort of a hint at how that's done, here's an experiment they actually do where they have a rat or a mouse, I think it's a rat, move along a path. So because the path is elevated, they can only move along this path, and they vary from the start position. So the rat is initially in this box, and then the door is opened, and the box is at different locations along this path. The rat knows that it gets food when it is there, so it's motivated to go there. So through this, you can actually vary how long the remaining path is, and you can do the reverse, where you start the rat here and have it move different distances into the box. And so what you see here is a correlation between cells, and there are two conditions where the environmental conditions differ, but that's not important for now. So this is just a vector of a lot of cells that are being observed in the system. It's not quite actually. So you have a lot of electrodes. McNaughton is actually famous for developing electrode array. So you stick electrodes into the midbrain of these animals, into hippocampus and adrenal cortex, and you can record from a lot of neurons simultaneously. That gives you a vector of neural activities, and this is a vector built from neurons in a particular part of hippocampus called CA1. And so what you do now is you correlate that vector, the activation in that vector, under different conditions. So you have the vector that you have at the initial position with a vector at different positions along this path. And this is just a correlation vector that, how well do these two vectors correlate? And then you do that along different positions, and then you can see if the point of maximum correlation, that will be the predicted shift between these two vectors, where that lies. And you can see that that sort of predicts where you are along that path. There's some details that are more that I want to gloss over. So there's some kind of indirect evidence for the neural population containing information about where you are along a path. And then there is some good evidence that heading of the animal really matters, or actually that it is neurally represented. So first of all, this is schematic, but you can have tuning curves, and I'll show you experimental tuning curves in a moment, where you look at the firing of neurons in a certain part of hippocampus as the animal is in a particular location and is heading in different directions. Actually, strictly speaking, a head direction cell. So the animal, as it is turning around, you're just measuring the head direction. You actually have some markers on the head, physical markers, and some movement measurement systems like we have in our lab. And you can therefore track the animal's pose and movement. And the behavior variable that you correlate the firing with is the orientation of the head in this environment. And the animal tends to follows its head. So if it turns the head, then it will be moving in that direction. So the body follows the head. So heading direction and head orientation is actually, and head orientation correlate. So it's actually used interchangeably in these papers. And we mean by heading direction, of course, really how the body displaces itself, but the head on the rat is an indicator of how it will be moving its body in space. And so what you find is that there are cells that are tuned to direction. So it's shown here in a polar coordinate frame centered in the head, so that different directions in which the head could be turning. And then the amount of firing of these cells is here on the radial axis. So this would be, for instance, a cone that reflects that in these directions, when the head is pointing in these directions, the cell is firing a lot. In other directions, it isn't firing. And here in this picture, these are actual measurements of head direction cell like that. So this cell is firing primarily if the head is directed in this way, and this one fires in that direction. So it stands for a certain heading direction. So with mathematical models actually of this that are based on the neurophysiology of hippocampus, essentially are neural field models. So they, for those of you who've been there in the winter semester, it's really the things that we discussed there. There is a peak of activation in a population of neurons that all stand for different heading, and there's a peak that is self-stabilized by interactions that represents that heading. And then actually these researchers propose a particular way how information from the motor system can shift that peak as the rat is turning. You can imagine when there's some kind of motor command that could make an input that is a gradient to that peak, and that would make the peak move and thus reflect the current heading. So it's an integration device, integration of rate of change of heading, reflecting then the heading. So that's a good argument why heading is a biologically meaningful variable. The other famous things, and this is what these folks, some of these folks, the Mosers, got a Nobel Prize for, was the discovery of these two kinds of cells. There are actually two groups. There is a couple, Moser, and the third person is it O'Keefe, I think, right? The third one, I think, is O'Keefe. They discovered two categories of cells. So one category is in so-called entorhinal cortex. That's a part of cortex that is projecting directly onto hippocampus. This hippocampus is a subcortical structure deep in the brain, the midbrain. And so that's very surprising. It was initially hard to believe that these cells in the entorhinal cortex fire in particular places that form a regular grid. Like this, the red spots are locations of the animal in a terrain where these cells, this particular cell fired a lot. Here's a different one, fires in these spots. This one fires in all those spots, and you see different fires a little bit in different spots. So these different patterns, grids, differ in their grid size and the angular orientation of the grid. Here's a theoretician's version of that. And this would be possible different grid cells, for instance. So they initially, it took some years to establish that. They initially thought it was an artifact because it was so strange. It would be such a regular pattern of the animal moving around in the terrain. It's like a little cage, right? It's an artificial system. You're recording from these animals, and there's a cable coming out of. Now they have, I think, wireless connections, but it was with a cable running the animals. It's a chronic animal that it has this implant. It's very easy to implant, and they can live with that. And then you're recording this while it's moving around, just kind of mind-boggling. But so they had to actually scale up the size of the terrain to make sure that it's really on a regular grid pattern. It did turn out this has been reproduced many times. Really true, there are these grid cells. The other kind of cells that I think were discovered earlier are in hippocampus. I forgot if it's in CA, where in hippocampus, but somewhere you find these so-called place cells. So for instance, actually, I'm not sure this is a very good example, but this is perhaps one where it's not a regular pattern. It tends to be a pattern that is even like single humped, that is one preferred location. Sometimes it's a little bit of a spatial distribution, but there's certain locations in the space where they would be firing and not somewhere else. So it's sort of like our peaks in our fields can be broad, it can be deformed, and they would be firing them. That is what is called a place cell. In a lot of these cases, there's also tuned for heading direction. So one thing I want to point out, you see all these little paths. These are the paths the animal made, some measurement system on the animal, as it was roaming around this territory. And that's sort of the subtlety. I mean, what you do in this experiment, and my colleague Bruno Pousset, not Pierre, his name is Bruno Pousset in Marseille. He had a lab like that, and I was there sometimes. And what they do is they motivate these mice or rats to sample space by throwing little foot pals into them. They're roaming then and eating these foot pals. And this is a very well-known environment to them. It's just a little circular cage typically, and there are no predators and anything. So they are very used to that. And so they go directly to the foot pals. They are not hiding and making a little excursion to get a foot pal and back to hiding as they would under natural conditions. And so that's really just to sample space. And that's these black trajectories show all the little roaming movement the animal did. And that's how you then can actually pick up that these cells fire when the animal's in different locations. Remember, the animals really just going for the food, always using olfaction. And while they do that, these cells really represent where they are. There's a lot of very interesting subtleties about that. So for instance, these place cells, just to tell you this one story, when you put the animal into this terrain, there is a lot of stuff with olfaction. These animals use a lot of olfaction, and that can be a complication. So you have to do things like change like a piece of paper and change that, or put something that kills the smell. But if we neglect that for a moment, then what will happen is, as you put it into the arena, the animal would be building a place field. That is, some cells you're recording, you suddenly start to see it's always firing in certain locations. And it turns out that pattern then persists, even if you, for instance, turn off the light so that the animal cannot use vision to reorient. Or what you can do is you can, for instance, turn off the light, and while you do that, you rotate the visual surround. You have maybe something on the outer boundaries of the box that make some pattern, and you just turn that a little bit and turn on the light again, and then you find that the place cell rotated with that visual surround, so that it now fires in a place that has the same relationship to that visual surround, but it's rotated over absolute space. So it's somehow visually locked, but when there's no vision, it still fires. So it's not just driven by vision, it's driven by the reckoning part, but it can also be reset from vision, just like the system I just showed you in our naive little model. So integrating or fusing these different kinds of information. These animals also use auditory information. So there are always some sound sources. That's actually difficult to control in experiment. So when there is some sound source, then they can detect the direction of that. And again, they are locked to that. So if you rotate relative to the sound source, the place field will rotate with that. But if you turn off the sound source, it still has the place field. It's a multimodal neural representation, can take input from different sensors. Olfaction very likely also plays a role, and the motor system plays a role. So very interesting phenomenon. You can see why that was worth a Nobel Prize. So here, just want to point out how this is connected to our kind of neural dynamics. Now, for those of you who did not listen to the winter semester lecture yet, you don't know the neural field stuff so well and so on. So I'm just sort of alluding to intuition, while the others might recognize that. So for instance, if you have multiple different grid cells, this is from a model, multiple different grid cells, then you're in a particular location, then you can imagine that when you're in a particular location, these different patterns will overlap optimally only at a very small subset of these grids. So here, this is the superposition of the firings of all these different grid cells at a location, at a particular location. And you see that then it's a very strong vote for one location. So if you put that through a sigmoid, you can actually estimate where you are. And that's how these grid cells can provide that estimate. And so what these people do is they show that how you could do that reckoning, that is, you could use this neural map of heading direction. So it would be a three-dimensional neural field, have a third dimension that is heading and a two dimension that are position. And then through the interaction of these two, this one would provide input to this one. You could make the peak move in this three-dimensional space. And they even propose there is some kind of periodic boundary condition so that when the animal moves beyond the boundary, it wraps into the same place field again. So that's sort of a theory of how the cells that we know and some of the neural mechanisms we know could give rise to navigation, to knowing where you are. This is not yet about how you recognize locations. Good, so that's the neural story behind the very old naive model that Axel Steinhagen and I did many years ago, but it's quite a good match. Now, last story, I want to just point to, in the last minutes here, I want to point to how some of these ideas have radiated back into technologies, kind of really a fascinating story, a very good example of neural ideas and technology ideas interacting. So there is a lot of work on SLAM in robotics and autonomous driving, as you might imagine. In fact, as I hinted in my introductory lecture, a major breakthrough in autonomous vehicles, autonomous driving, came from new methods of doing something like SLAM, specialized SLAM for driving in cars. And this was based on probabilistic approaches. I didn't say this in detail, and laser rangefinders. So laser rangefinders give you very simple sort of views. The views are 3D, like depth profiles, right? You would have depth profiles as your 3D environment, and then and you can use them also to do collision-free driving. And then you could do SLAM using probabilistic methods, which I didn't explain, but that was a major breakthrough in these people who did the dynamic window approach. Sebastian Thron in particular, and his colleagues Fox and the one from Freiburg was Burkhardt. They were really leaders in this and developed methods that are now used everywhere. So that improved a lot the capacity of autonomous vehicles to do map formation, and especially to self-localize within maps. And that is really being deployed today. So there are systems that work like that. And there is a group in Australia around Milford who do the same sort of thing, but really with biological ideas. So they literally use what I just viewed, local view cells and these pole cells or head orientation cells and place cells on the three-dimensional space orientation or heading and position, and I'll not explain the details, but essentially like in the neural system to do path integration. And then they also combine that with, so primarily to do this for visual odometry, that is to use this to update the estimate of where the system currently is. Essentially, and I can't explain the details of that. And they also connect that to landmark recognition. So first, let's talk about this integration. So here's an example. This is literally what they call a rat slam. It's kind of technical rat. That's a little toy example that's moving around an arena like that, where it has views like that. And they show that just sort of based on these biological ideas, just taking these views, taking this hippocampal-like structure, implemented algorithmically, it's not neural dynamics, but using neural ideas, they can make the system build a map of that environment. So here is the map after some time that system built of that environment. You can see how it qualitatively gets the topology of this quite right. And I think this is the final value where it thinks the robot thinks it is. Pretty cool. And they scale this up. This is a car moving around a territory. I don't actually know what kind of car, what kind of vehicle. I believe it's a car or some kind of vehicle. And so after a lot of time, it did build a map, self-organized map. You see, it's a little bit off here. There's some rotation. This is the typical thing that happens, right? That there's some global orientation error. And this, as long as the system is able to close the loop, that is to find back to this entrance, that's okay, because it doesn't have to be an absolute map, right? It's just within the map it can orient, it can find where the path is. So there is some orientation error happening here, but the topology is quite right. This is after a considerable amount of time. And this system is really being used technically now. This group has also a very interesting, this is typo here, Milford. It's the same person, Milford is an F here. This group also uses spiking vision sensors. So neuromorphic hardware, I think I haven't talked about that yet, but there are some people, including some of my former students, who are in the business of using analog computation, different forms of doing that, where you're emulating really visual sensors and biological vision sensors like the eye, that sensor spikes, and these spikes actually only happen when there is some change in the visual array, which gives very interesting possibilities because you have to transmit much less information. You don't transmit a whole picture with most pixels not changing. You only transmit any changes, sort of like in the MPEG compression algorithm, but this is really on the periphery. The sensor itself only sends signals where there's change, pretty much like your retina does. And when they do that, then they can try to implement this correlation issue that I was hinting at, where you're taking your view, represented now by a batch of spiking events, so a matrix of spiking events, and you have a stored representation of that, and you're computing essentially synaptically, in the way I was hinting, the correlation, and from that you try to recognize the view. And there's a whole line of work, it's quite recent work. So for instance, this is a system that has done that gets this view, a really pretty bad view, right, from a car mounted camera, put that through this vision sensor, and then they make a reference. So for instance, this is a view that they have stored, and this is reflects a bit the match. So they really were able to say this must be, is a variant of this view. I don't remember exactly how that's actually done. And similar, here's a success story. Well, there are two examples here where it actually picks out the wrong view. This would be the right view, and it actually picks out this view, which isn't isn't the right one. It's a different location. There's some errors here. But so I'm just saying it is possible with actual physical hardware to solve this place recognition system in a somewhat neural style. This is ongoing research. It's not deployed or anything. This is current research in this direction. And this group of my former students, led by Julian Zanimirsky, who's sort of the group leader, has done that for a subproblem of that. So essentially, it's SLAM for heading direction. It's a robot that's looking around, and there are literally neural fields in our style that are discretely sampled, and they're implemented on a neuromorphic chip. So they're not numerically simulated, but actually done on the chip very efficiently. And that enables a robot. This is this ICOP experimental robot that is, in this case, just looking around, and you're just proving that you can then use vision to provide a path estimate of where the system is looking around. This is sort of a time course of these spike trains. You see these dots of little spikes. And all I'm saying, you can. So there is some way how to compare that. I don't even know. The system can do that. That is, can take these spikes that are generated from the vision and to compute the estimation of change that explains the change of the visual array, and thus estimate the pose of the head of that robot. So just a point of this direction, how you could put neural technology, maybe ultimately to the real world, inspired by animal navigation, how animals estimate where they are. So to conclude, navigation entails both knowing how to get places, but also really knowing where you are, and therefore where places are relative to you. And so what I illustrate in this one example is that one can do all of that with dynamics. Behavioral dynamics would be essentially these, when you have these action kind of what we call behavioral variables, but in other contexts, you need what I didn't explain here, neurodynamics. So in the example I showed you, I would call the estimation procedure also behavioral dynamics, because you're really estimating a state, a physical state like position, and updating that and heading direction. But the decisions on when to make a home base and how to recalibrate and so on, that is actually based on neurodynamics that I didn't explain, what I call behavior organization. And so the important thing in the navigation problem is that you will have to occasionally reset your location. It cannot be based only on integrative, integration, which is a simple form of dynamics, and that is based on instabilities. And I showed you this one example. I didn't explain it very well. And the typical sensor information that triggers such instabilities is some form of recognition approach. Now, with the semester, I'm teaching you that recognition can be done with neurodynamics, but of course, in most cases here, it's done by regular neural networks, forward neural networks. And that's one of the insights, that these recalibrations can be based on somewhat meaningless things, just 3D views, or in some of these technical applications, really just depth profiles without any object recognition or segmentation or ascribing meaning to parts of the scene. It can be just raw sensor information, and just by associating that sensor information with your estimate of where you currently are, the net effect of that will be to be able to enable self-localization and map formation. And then in that case, particularly clear that the discrete nature of that you recognize where you are in different moments in time, discrete moments in time, that is an emergent property. In our model, it's an emergent property that comes from the instabilities. Other systems do that somewhat more ad hoc. Good. That's as far as I want to push this today and close this lecture.